My name is Fridovich-Keil, and I'm excited to present our work proving a recovery guarantee and efficient algorithm for finding sparse neural networks. Prior work has shown that sparse neural networks can often match the accuracy of their dense counterparts while using far fewer parameters. However, actually finding these sparse, high-performing networks remains challenging. Many methods exist that trade off computation time, memory, and accuracy, but to our knowledge, none of these approaches come with theoretical guarantees. To bridge this gap, we leverage a connection to compressive sensing. Say we have a large unknown vector x, but we are told that most of its entries are 0. We get to take a small set of linear measurements y, from which we want to recover x. Compressed sensing tells us that if our sensing matrix A satisfies certain properties, then we can uniquely identify the full sparse vector x from a small number of measurements. Moreover, this recovery process can be done with memory linear in the number of non-zero entries in x, using a simple algorithm called iterative hard thresholding, or IHT. IHT is essentially gradient descent, with the restriction that we only keep track of the largest magnitude entries in x at each iteration. To leverage this result for our goal of finding the weights of a sparse neural network, we need to reformulate our two-layer MLP training process as a linear sensing problem. Let X be our training dataset, with n examples each of dimension d. If our MLP has hidden dimension m, its hidden layer contains m neurons, each with a weight vector uj of dimension d. We assume the MLP produces a scalar output, so its output layer is a single vector v of dimension m. The function computed by this simple two-layer MLP is shown on the left, with the subscript plus used to denote ReLU. We can reformulate this by writing out the ReLU explicitly, using an indicator function. Now we simply expand the sum over the m neurons into matrix notation, and observe that the output of the network is just the product of a wide matrix A with a tall vector containing the weights of the MLP. Let's visualize this in the same format as the standard sparse recovery problem from compressed sensing. Now the sparse vector x that we want to recover is just the concatenated weights of the sparse MLP. The measurements y are just the training labels. Let's look more closely at the structure of A and its dependence on the data. For simplicity of visualization, assume that each training example is a scalar, so d equals 1, and we have the training dataset capital X shown in the bottom left. Every column of A is just a copy of this dataset capital X, masked by some activation pattern that sets certain entries to 0. These activation patterns depend on the neuron weights u, which we don't know, so we simply enumerate over all possible patterns, indexed by vectors h, to form a very wide matrix A and a correspondingly even sparser vector lowercase x, which has zeros corresponding to any activation patterns that aren't in the true network. Now we are ready for our main theoretical result. Assume that we are given a dataset of training examples capital X with labels y, and we are told that this dataset is consistent with some two-layer scalar output MLP with no more than s non-zero weights in its hidden layer. Then the resulting A matrix satisfies the conditions from compressive sensing that allow us to run iterative hard thresholding and recover the sparse network weights exactly, using working memory proportional to the number of non-zero weights. To our knowledge, this is the first theoretical result of its type, that gives both a recovery guarantee and an efficient algorithm for training sparse neural networks with limited memory. We provide some small-scale numerical experiments to validate our theory. First, we create a dataset using a planted MLP, so that we can be confident that the training data is perfectly consistent with a sparse MLP. We vary the hidden dimension m and the number of non-zero weights s, and plot a heat map of PSNR using our iterative hard thresholding as well as the iterative magnitude pruning strategy proposed in the lottery ticket hypothesis. We can see that IHT performs much better than IMP, even though IMP requires far more memory, enough to first train a dense network. We also test both algorithms for binary MNIST classification, distinguishing digit 0 from digit 1, and find that IHT can find successful sparse MLPs for this simple task even with only a single non-zero neuron weight, while IMP requires dozens of non-zero weights. We also test both algorithms for the task of fitting a sparse implicit neural representation of an MNIST image. This involves first applying a Fourier feature embedding to the pixel coordinates, and then treating these embedded coordinates as the input to a sparse two-layer MLP to predict the grayscale value at each pixel. IHT achieves accurate image fitting using only 100 non-zero weights, whereas IMP struggles to capture an MNIST image even with an order of magnitude more parameters. Please refer to our paper for full details and additional experiments. Thanks for listening.